Hello. In this video, we're going to talk about the KSP, salts, and what is KSP and some problems. So let's get started with a beaker. This beaker has a salt crystal and add some pure water. So the pure water is the solvent, and the salt is silver chloride, and it's going to dissolve, right? So how does it dissolve? With the thermal energy in the water. So even it's cold water, there is thermal energy. Now, so this starts breaking into cations and anions, or we call the dissociation, right? So the cations, I call the cation, see the plus sign, and also anion, negative for the anion. So like an, right? So the cations and anions are produced as a result of the thermal energy. So these ones are called the ion products. So your reactant is the salt, the solid. There's no molarity for it, but your product is ions. So let's look at a couple of salts. So the salts are actually metal cations and non-metal anions together with the electrostatic energy, keeping together as a crystal. So there are two kinds of salts we need to know. First one is fully soluble, and the other one is we call the insoluble, or we call the sparingly soluble salts. So the fully soluble ones are, examples are sodium chloride, the table salt, breaks 100% into ions. And the silver chloride is actually breaks less than 1% into its ions of silver plus and chloride minus. So that's the fundamental difference. So fully soluble ones and the insoluble ones. The fully soluble ones are actually lithium to cesium in the column downward, and this is the first column. So the first column and salts, first column salts, and the ammonium and nitrates are fully soluble. So in this table, you need to know how to read this table, right? So this table, you can see the first column metal salts and the ammoniums and nitrates are fully soluble. No need to do math on these. Now, let's look at the other ones. All these silver, lead, and mercury and other salts are precipitations. They do precipitate, right? So we need to do KSP math on it. So let's look at a bit more details. So you put a crystal, or bunch of crystals actually, into pure water. It's going to start dissociation. And so what's actually happening, the solid breaks into ions of silver plus and chloride minus. So this is called I call the dissociation. So it makes the aqueous ions. So dissociation, simply I call the dissociation, breaks into ions. And we can graph it with the rates of the dissociation versus time. It's important to understand this graph. So at the beginning, your crystals are breaking super fast into ions, and dissociation will be very high at the beginning, and then it slow down, right? And there are a whole bunch of ions after some time. Now, when you have a whole bunch of ions, it's gonna start precipitation. So I call the PPT. So that it starts making PPT, or precipitation, that starts from 0 to upward. At some point, these two, dissociation rate and the precipitation rate, is going to meet together, right? So beginning dissociation is faster than precipitation, and later precipitation picks up the speed. It's the reverse of the previous one, right? So now once we have the two rates are equal, that's the time you have the equal two arrows, remember? So that's in the equilibrium also the same. That's an equilibrium. The two rates have the same value, right? So this equilibrium is special, right? And normally we're talking about that equilibrium happens at 25 degrees in the water. We call it KSP for a salt, right? in the water 25 degrees. It's important. So that's the only thing you're going to be doing math for it. So the Ksp is actually equals to ion products. So normally it's coming from product over reactants, but it's ion products. So this is also we should call saturated solutions. So equal rates, Ksp and the saturated solution, it's same idea, right? Let's look at what's happening in the beaker with a given timeline. So if I get 4 snapshots, so from the very beginning and after some time. So very beginning you have salt, solute and pure water, then start dissociate, and it keep dissociating and adding more and more cations and anions. Eventually it's going to settle some precipitation in the bottom. So that's the final one. So that has a, so look at the arrows, right? So if you look at diluted, concentrated, saturated, it will show first you have a lot of dissociation and then the equal rates, right? So that's another way of looking at, and also explanation of solutions, diluted, concentrated and saturated. Now we're going to do some other questions. So this one I call the type 1 or AB type. Sometimes you can call BA type, it doesn't really matter. So silver chloride goes into silver and chloride minus. I call this one is a Rice table. So normally you know ice table, it's the same thing, but I add the ratio because it's important for your math. Ratio is 1 and 1 and 1. So initially, so we have also, we can actually pictorially you can show silver chloride is a plus and a minus, and you dissociate into plus and minus. So that's why it's 1 goes to 1 and 1. It's not 1 goes to 1 plus 1. Okay. So initially we have some solid, some crystals, right? And then solids don't have a molarity. I just put a box there. And initially no ions. And then if you lose S amount, you're going to get S amount and S amount. So the equilibrium is solid minus S, right? Now, so look at the dissociation of ions. What's the most important thing is the equilibrium. The solid doesn't count, so disregard solids, and then minus S goes to S and S at the equilibrium. Let's write an equilibrium. KEQ is product over reactants. That's what you always do. In this case, reactant is a solid. We forget about the reactant, right? Then we can say constant of solubility product. The products, the ion products, right? Now, in this case, the ion products are silver plus and chloride minus, cations and anions. You plug in the SR 0.2, 0.4, some molarity. So these are circle brackets and S squared, S times S. Ksp is S squared. This AB type is Ksp equal to S squared. S is solubility. I will explain a little bit later solubility more. So given the S, you can just get the square of it, you will get the Ksp. So that's a straightforward question and answer if you are doing a problem. How do you go for the reverse? Given Ksp, how do you get the solubility, the S? Sometimes you call it X, but S is better letter for it. So the Ksp equals to S squared, right? And then you times by the root of each side. So you cancel the root to the S squared. You get root of the Ksp will be given by, to get your S, the answer you need. And the Ksp, there is a table, you can look it up. I'll show you in a moment what the table looks like, right? And how to read those tables. Now, so we have the second type. I call the AB2 type. Sometimes you can call A2B type. It's the same thing. So this one, good example is PbI2 and dissociate into Pb2 plus and 2i minus, right? Now, we can write the crisscross rule to get Pb is a 2 plus and I minus. So that's how the ratio, the important thing is 1, 1, 2 ratio. Initially 0, 0, lose minus S, gets S and 2S, right? And equilibrium minus S goes to S and 2S again. So we can write the Ksp is the ion product and the ions are Pb2 plus square bracket for the molarity, I minus the 2, that ratio 2 goes there as power. That's the coefficient, the power. Now, you also plug in the numerical values of S and 2S into this formula, then you get this. So S times 4S2, that means altogether it's a KSP is 4S cubed. So that's the formula you're going to memorize. So given the S, you can calculate the KSP. Just take S cubed times 4, right? Now, how the reverse? So the reverse is a little bit similar to the previous one, and we can just do the math, the breakdown, how you take it, right? So given KSP, how do we get the solubility, right? That's also the molar solubility. KSP equal to 4S cubed. So divided by 4, you get KSP divided by 4, 4S cubed divided by 4, cancel the 4, voila. So now you take the third root of each side. So KSP divided by 4 third root to the S cubed cancels out, voila, you get S. So that's how you get the S, the answer you need, third root of the KSP divided by 4 inside the bracket, right? So the brackets are important when you use the calculator. I'll show you in the example. Now, let's go to the third type, AB3 type, right? It could be even A3B type. It's similar, right? So iron hydroxide, iron 3 hydroxide actually, you can break it down using the crisscross rule, and look at my crisscross rule video if you have trouble. So ratio 1, 1, 3 in this case, and equilibrium is minus S, S and 3S, and that's all we need. KSP is iron product, plug in iron 3 and OH minus, take this ratio, the coefficient power of 3 there. Now, so plug in the numerical values of S and 3S, and S, it will become 27S to the power of 4, KSP equals to that. That's how the S given, how you calculate the KSP. Now you can do the reverse as well, similar to the previous one. I don't think math part is really important. Just try to memorize this way. You can take the fourth root divided by 27, the KSP, that's inside bracket. Now, the more important thing is molar solubility, the S for the solubility. That's given in moles per liter, big M, right? So, chemists use the molar solubility, but sometimes engineers and city people, techs, use gram solubility, grams per milliliter, right? That would be grams per milliliter. You can get the molar mass or formula units, and over moles, you can cancel the gram. Voila, you get the moles over liter, the big M, right? So that simple math we need to practice. Now, let's look at given the gram per milliliter sometimes, how do you convert? 1000 milliliter is 1 liter, and 1 mole is the molar mass or the formula unit. You plug in and you will get the molarity, the S, molar solubility. So you want to cancel here mil to mil, gram to gram, voila, mole over liter, the big M, the molar solubility. Then you can plug into about 3 formulas and you can solve most of the KSP problems. Look for my problem solving video next, and then you will be fine with the problems, right? So I'll give you 3 examples for it. Look at how to read the KSP values from a table, right? So here it is, it's 25 degrees. Look at you can find AB type, you can find the KSP. If you know the KSP, you can calculate the solubility. You can find A2B type, you can type AB3 type, all these things you can find and do the math. Thank you.